So the last part in this example is going to rely on a proof by induction for the statement that we said earlier, that n times n plus 1 divided by 2 is the sum of the first n integers. So let's go ahead and begin the proof by first saying the proof in this case is a proof by weak induction again. So I'm just going to write down proof by induction, and I'm just going to let n be this time an integer. And the requirement is that it has to be more than 1. Okay, so n is going to be more than 1. This is implied because they said the first n integer, so it doesn't make really much sense to start with anything else. So I'm going to go ahead and begin with the base case. So what am I doing with the base case? With the base case, I'm doing n equal to 1. That's the beginning of my domain up here. And on one hand, I know that if I add 1 to, well, nothing to itself, I get the 1 back. So that's great. And next I'm going to test the right hand side, and the right hand side is pretty much the right hand side of this up here, the n times n plus 1 divided by 2. So let's find out what do we get. We get 1 times 1 plus 1 all divided by 2. So this is 1 times 2 all divided by 2, which is equal to 1 at the end. So it seems like so far everything is working out. So this statement is true. So base case is safe, and we can now go ahead and move on to the inductive hypothesis. So in the inductive hypothesis, what we're going to do is suppose that the sum of the first n integers, so 1 plus 2 plus 3 plus so on and so forth all the way to n, is in fact equal to n times n plus 1 divided by 2 for some random n equal to k. So for some random integer, we're going to suppose that this statement is true, and we want to show that the statement holds for the next guy. So I'm going to go ahead and write that down. So I'm going to say I want to show that the theorem or the statement, the proposition, the conjecture holds for n equal to k plus 1. So in other terms, here's what I want to show. So i.e., in other terms, I want to show that 1 plus 2 plus 3 plus all the way to n and the next guy, n plus 1. I want to show that that is the same thing as n plus 1 times n plus 2 all divided by 2. And so that's my, basically a little comment to myself. And now I'm going to begin to do that. Okay, so to begin to do that, I'm just going to start with the left-hand side. So the left-hand side is basically all of this stuff. I'll go ahead and write it down. Matter of fact, you know what? I'm just going to grab it real quick, do copy paste, and just put it right there. Okay. Now, that's the left-hand side, which is great. Now, out of this left-hand side, the 1 plus 2 plus n plus whatever, that is because of the inductive hypothesis. We know that that's the same thing as n times n plus 1 all divided by 2. That's what we pretty much said up here. We said that 1 plus 2 plus 3 all the way to n, that's the same thing as n times n plus 1 over 2. So you know what? I'm going to go ahead and highlight it with a different color so that we can kind of see where we're using it. Okay, so we used it pretty much down here to replace that summation. Now, there's also the additional n plus 1 at the end, which is just going to be hanging out for now. Okay, well, it seems like we have a term with a fraction and a term without a fraction, so maybe it's a good idea to put a common denominator and then have n plus 1, and then the common denominator is going to be basically 2, so we need a 2 times n plus 1 right there. And by doing a little factoring, I can pull the n plus 1 out. So think of it like one box, a second box, the two boxes both have n plus 1s, so we can pretty much factor it out, and when we do, we end up with n plus 1 times n plus 2 rather, and all divided by 2, which is what we needed to show in the first place. Okay, so I'm going to write down which is what we wanted. Okay, as a matter of fact, if you want, there are times when we just do this. We say it is actually, in fact, the right-hand side of our conjecture. And that's what we wanted, so we're just going to say QED by induction. Okay, I'll see you in the next video.